As far as today's problems go, some people that would like a little more time, so if you can turn it in by Friday, you get full credit. If you want an extra 5 points, you can turn it in now, today, so give you a little bit more time. Okay, we're in the middle of the description of the complex variable shortcuts to various physical phenomena, particularly ones that involve electric fields, say. The thing that I should point out, and I'll do that again when we talk about the next function that I want to get into, which is 1 over z. The idea of making a surface such as this one to show, in this case, the scalar potential is being plotted, and it made a hyperbolic saddle in the xy space with all of the contour lines, first the red ones for the scalar potential, and then the blue streamline vector potential lines in a 3D setting. It is set right now, so if you do the trick with the finger and somehow get your brain to put these two images on top of each other and be able to focus on the screen, that was a trick I told you about before, then you can see this much more clearly. But the other surface that we can also plot is the vector potential. And I'm just curious how many of you can actually do that interocular trick and get the thing. I can do it from the side without even using my finger. But it's because I've looked at these things so many times. It takes a little bit of practice. In any case, in the textbook, all of these things are set up on the page so that it really matches the. It's a little bit shorter than the average interocular spacing that people have. And so just bring the textbook page to the point where one eye is right on top of the image that belongs to it, and then slowly pull yourself back and let the focus take over so that you actually have a sharp image. And then the two things you don't want to look at are sort of off to the side, but the 3D image jumps out. That will help you with some of these wild surfaces. We're making it, as I said, TC is getting an application that works on the browsers, and it's going to have a lot more of that and a lot more functions, a whole bunch of things that you can do that tie in with the stuff we'll talk about today. Okay, I'm going to do a review of what it is that we remember that I'm going to keep this computer quiet and just use the old guy that's hiding in that machine right there. So basic idea of what we're making here using complex variables is a set of vector fields. That's the things that are written as a lowercase f. Those are the components that would be what we're actually plotting in a number of different ways. But in particular, the idea that by making just picking a complex function, in this case the f of z equal z, gives you well, it's what we'll see as it's a kind of a quadrupole field that has these hyperbolic energy surfaces, the scalar energy surface and the vector energy surface. I'll go ahead on this app right here and plot the 3D picture of the vector potential. And you see it's also a set of, it also is a hyperbolic saddle surface. But now the axis that has the A attached to it, that is, the plot is x and is the vector potential A versus x and y. The contour lines now are for constant A, and the flow lines, bloody flow in the streets or something, that they are perpendicular to those and serving the role that these guys served before. So it's an interesting flip that happens here, and the saddle is turned relative to the saddle that would have been plotted just a minute ago when we do the scalar phi, uppercase phi plot. But anyway, before we got into potentials, we just made sure that the field that we get by picking the particular f of z, as I say, just choose an arbitrary function, f of z, and conjugate it. Change all the i's to minus I, so that you're plotting f star versus d star, really. And that particular function has 0 z derivative, and therefore it has 0 divergence and 0 curl. So the first field that we took was the one that goes with this, and I'll just go back to that one right now. Find the cursor. There, and just plot this thing right here as it was before, with all of the contour lines in the place that they occupy when you look straight down the axis of either one of these plots that we just showed. So basic idea is that the field that we have produced has no divergence and no curl. You check the divergence by seeing if any contour that you draw has more strength or length of vector as it comes out of in other words, you tally the amount of vectors that are pointing into the surface and correlate them to their position relative to the actual contour, and see if the field is picking up strength. That is it diverging, and is there something there producing stronger field vectors? And the other thing that's also 0 is the curl. You see, if you draw a contour around here, is there a tendency to rotate? Are the vectors on this side stronger than the ones on this side? And also, well, does the line integral actually give you anything when you do an integral of the f dot, the differential of whatever contour you have? So it may look like these are diverging, in some places it may look like they're curling, but this is definitely the case, that giving 0 this and 0 that, if you follow this little recipe. So what I'd like to make a point of is that this could be flow of water, could be flow of what they call dry water. It could be an electric field, and these are the voltages, the red lines there. Could be heat flow under certain situations, which will become clearer as we discuss where are the sources for this. And the way to visualize the source, which is at infinity, is to put this all on a sphere, and then the sources are all located. If this is the North Pole that we're standing in, they're down in the South Pole. And that's what we'll be getting to later on as we discuss this particular type of geometry. Okay, now the picture, of course, that we're looking at is right there, and the divergences and curls check out to be 0, as we pointed out before. And the other thing that's going to be true is line integrals, or integrals of the complex variable function, either the force or the potential, whatever. But the idea is that the fact that the f of z is the derivative means derivative of the scalar potential means that the scalar potential is the integral. So we get to the integral of that very quickly. That's the shortcut of the complex variables. It really is nice at applying ordinary one-dimensional real calculus, works for complex variables as well, and gives us both the scalar function, which we plotted up there, and then this one, which we just finished looking at. And this is the top view of, well, both of them at once. And it's also a coordinate system. And in this case, an orthogonal curvilinear coordinate system, which is a subset of all of the generalized curvilinear coordinate systems we're going to have to work with a lot in the rest of this class. So, the idea then that you can get the field back again by taking a derivative, that is taking a gradient of the scalar or a curl of the A, both of those give you the same field back again. Now, this situation is kind of weird. This is very much like what we started with for our mechanics of the superballs. And that was, you had, say, just two balls and maybe some walls and a floor, or a floor and a ceiling, rather, and nothing in between that causes a change in velocity, right? We started off without mentioning force at all, and we just had the conservation momentum as our one axiom, right? And momentum is conserved because it's flying through nothing at all, and then all of a sudden, crash, a collision of some kind occurs, velocity changes, there's lots of force involved in that, but we had ways to handle that without even talking about it. Well, this is a similar thing here. All of these things are flowing in some sort of vacuum, and nothing new is being produced or taken away from these field vectors. And what I want to discuss at the very end of this lecture today, it's just kind of weird, and I haven't seen it anywhere else, but it's kind of fun to play with, and that is, how do you put the sources, if you have a continuous set of sources, how do you get them into this? And the idea is you use non-analytic functions. So it's the analytic functions that are giving us source-free fields. That's kind of the way to state this. Okay, now let's see if there's anything else. The algebra of this particular thing and the reason for that symmetry we saw are those conditions right there. Turn the thing inside out and have a conjugate set of conditions, but that's not something we need right now. And also I want to make sure that you understand that if these things are a function of, well, we're taking them as a function of z at first and then plotting the things that are functions of z star. If it's just function of one of those, it's an analytic function of that variable. In this case, we're looking for analytic functions of z. And the most famous one in quantum mechanics, psi star psi, not an analytic function of psi, the variable psi. So that's something to keep in mind when it comes time to look at some of these complex calculus or scattering problems in quantum mechanics. Anyway, the integrals that define the real part, the plain old line integral, that is the integral of force dot dr, or the opposite one that goes in the imaginary slot, that's the other kind of integral, and that's the flux interval, how much of a field is crossing a contour. And the idea, of course, is that no matter what the contour is from a point to point, you don't have to do the integral. You simply have to take a difference if you're interested in the change in the voltage, the scalar potential. You just subtract them, and you do the same with the vector potential. Now remember that I do boldface notation with a and even phi. That is a single variable, is not two. It's a real variable, single real variable, because we're dealing in 2 dimensions, and the A value, the thing that determines which of these contours you're on, the vector potential contours, is a single variable, just like phi. Okay, and then there's a better picture for looking at on imagining a contour. And that's something else that will be much better in this program that we're putting together using JavaScript. Okay, what else? Curvilinear coordinates. Let's make sure we make connections, in this particular for the problems that are being handed out today, both the Jacobian, and here we are, x and y, versus the queer coordinates. Well, the queer coordinates are phi and a. Okay, so our Jacobian is a pretty simple little expression there. Its units are inverse distance. But here are the covariant vectors, and they're pretty much the same as the contravariant vectors, which are gotten from the Jacobian, where I've taken the partial derivatives with the queer coordinates, namely the scalar and vector potential, in the numerator of the partial derivatives. And then the metric tensor here, this is really quite striking about the coordinate systems that you have here. They're really orthogonal, curvilinear, and have the same value on the diagonal and nothing off diagonal. The scalar vector E phi is always orthogonal to the A, and that's what makes it OCC. So that idea is really important here, and let me put it on both screens here just to make sure we keep up here. There is the and this is really important. This is the fact that both of these functions, and this is so important, I think I ought to put it on the other screen as well. Keep that one sort of constant for the time being. The fact that the scalar function, the uppercase phi, that gives with the gradient the force vector, and the A vector potential, okay, in this case it's just simple xy, whose curl is also the same f here, but either one of those functions satisfies the second derivative equation. It's called the Laplace equation. So you're very used to having the Laplace double derivative. The curvature, as we'll explain in a minute, the double derivative with respect to x, the double derivative, second derivative with respect to y of phi, absolutely zero. And that is easily seen, of course, for this very simple case. But it's also true for A. Okay, now what's going on there? What's going on there is a geometrical application of this stuff. It's really quite striking. When we're drawing those hyperbolic saddles that go with either one of these sets of curves here, we could be drawing a picture of a soap film on a wire that is one of the boundaries of the block. So that saddle could have been a soap bubble, and that would be a minimal surface. it would stretch to the minimum energy and be as small as it could possibly be. The soap would contract just by nature of that. And these are a neat demonstration. Now we're going to have an example in just a minute here. We take a source function, and I'll say more about this minimal surface business then. But that is what's going on here is that the sum of the curvatures, the x curvature, has to be the negative of the y curvature. So if I've got a thing that goes like this, then perpendicular to that I've got to have something that's going the other way. Something going like this here, I've got to have something going like this in the other direction. Sum of x and y has to come to 0. Curvatures have to sum to 0. So the surface has at every point a 0 sum curvature. Some people call this average or a mean curvature. Okay, that's the trace of the Jacobian, the Jacobian of the partial derivatives. The logical contrapositive of that is the Gaussian curvature, the product of the principal curvatures. That's definitely not 0 for most of these surfaces. But let's just talk about the mean curvature in just a minute when we get to that. Now, here is where the review ends, and we want to take a look here what it means to have a monopole source, the most elementary source which puts out the fields. In other words, things that are making these fields are collections of these things. And of all the power law fields that we have, one lacks a power law potential, and that's this guy. Of all the possible power laws that I can have, I make what will be called multiple functions, but this particular one, the monopole, is the only one that doesn't have a power law potential. And that's because when you integrate z to the n, you're hoping you get z to the n plus 1 over n plus 1. But if n is minus 1, you got a problem. Okay, it goes to infinity. Okay? So this is the one that gives you log root. Okay, very special case. Okay, well, it is special. It's the thing that's producing everything in this imaginary field theory. Good old monopole. All right, let's go ahead and work out the scalar and the vector potential that goes with this. We've got a phi, we've got an IA for every one of these things when we integrate. So we've got to turn this thing right here, a log z, into two parts. It's got a real part and an imaginary part. That's going to be our scalar potential, the real part, and then the vector potential, well, take the logarithm of this thing, that's what you're going to see there. So that product has the log of r first, and then it's got, keeping this real for now, but we don't have to do that, log of e to the I phi. That's just I phi. So there, that's kind of weird, and that's what we need to take a look at. Okay. So I'm going to go ahead and go to this computer over here and just pick a new field. Get this thing so it knows where I'm orienting. And this is what the CC has already made a much bigger list of functions than we've got here. But we've already seen force field that's constant, and then force field that's linear in z. That's what we've been working with. I'd kind of like to go over here and look right now at the very first one of these, the monopole. Now, this particular app will do this, and I think yours will too. It'll ask you if you want to keep all of this stuff that you've made by poking on this thing, and go ahead and make a new function with all that stuff. Usually that'd be a mess. So this is what I'm clicking right here to get rid of that, and then I'm going to have a plot of that field. We'll do just these phi lines first, but you see what I've got here are a bunch of arrows pointing away from the center. Now, at this point, you might say, my gosh, this can't possibly be divergence-free. If I draw a thing, I've got this great big thing drawing in here, and by the time I come out the other side, I got nothing. This looks like a negative divergence. And the answer is, no, it isn't. If you draw any contour around this thing, 0 is what you get for the flux, and 0 is what you get for the circulation. But in any case, if I'm going to plot scalar things, anytime I pick a point, that result over there tells me this is what I've got to get. So I'm just going to draw a number of the equipotentials, and then if I can make the cursor work, we'll draw these streamlines. Now, it should be pretty obvious where the streamlines are going to be. They're going to be, oops, that's a little, making two things that are close together there. Doesn't hurt. I'm not being careful in making them at constant voltages or anything, but I'd kind of like to have a really small circle there. Maybe an extra one in here. Because we're going to plot the scalar potential separately and the vector potential separately. Let's go back though and get a few of the streamlines. So the A lines now I'm looking for, so I come back and it remembers what I've plotted, and then, for example, if I draw a dot right there, I should get a line going through that, and so forth. So you can see the coordinate system that this is giving to us is the very simplest GCC. It's actually an OCC, of course, because that's what you get when you use these complex variable things. These are the streamlines in or out of the source. The source being located at the origin, where there definitely is a singularity. Polar coordinates has one singularity, and it's at the origin. And these singularities are things we have to sort out using the Jacobian, and that's what's going to begin next week when we do the lectures on mechanics. See if I get one close to the x-axis. Maybe one up here. Okay. Enough of that. Now I'm going to go over here and ask for, and this is, I'll use cross-eye again in case you can get a 3D look at it. I'm not going to plot the XY grid. That helps if you haven't made any lines yet. We're just going to plot the phi and A lines for the real part of this. And there's a nice 3D picture of that. And it might not hurt to zoom in by 2 here, make it a little larger. In any case, this has a really beautiful shape to it. And we've already talked about what a logarithmic curve looks like. The logarithm in any direction around the phi or z axis, vertical axis, and so it's kind of like a morning glory or something that we have here, and it gets real tight because if you turn your head on the side, you're looking at the exponential curve, right? And it just gloms exponentially onto the z-axis. Okay? Anybody got this in 3D yet? It's, so this is a good one to practice on because it's really obvious if you can do it. But that's what we're dealing with. We're looking down at the top of this source. This is the source, and it goes to negative infinity. And that's or you can make it pop up by putting a minus sign on this. Okay. So, let me come ahead on the other screen here.
When you view it at home, you could change the size and your position so it's easier to lock in. How many people have Google Cardboard? You do? A handful? That would be a way of viewing this in 3D.
Yeah, I don't even know about that.
Yeah. Talk offline.
Yeah.
It's burgeoning.
Yeah. Okay. Now, this isn't the only way to plot this particular example. The A, that's the one that really shows the structure of any integrals you're going to be doing in complex variables. If I plot this here, where I look at the imaginary part of our potential, that is the A, we get, kind of at first looks like a mess. I'll try to disentangle it a little bit here. And this is something that looks a lot better on the modern plot that TC is working on. But if you get a chance to, okay, there, I think we're getting a pretty good.
It's that branch that causes issues.
Maybe I should have gone the other way. But what you see is a circular staircase. And if you're looking at this in 3D, you're seeing a helicoid that is a half of a DNA molecule. There we go. I can line those up. You can sort of see what it is that this thing is doing. And remember, the red are the flow lines now with respect to this drawing. So that's what you're seeing when you look down. Now this is cheating here to make a vortex, that is to make the streamlines be a circular. I put an I here. If I put an imaginary source, okay, I'm producing what would be the B field for a wire coming out of the, a current carrying wire coming out of the screen along that axis. But I always put this in for all of our drawings so you see what it is that was being used. Basically, the logarithm now is the vector potential, and the scalar is the angle, just plain angle theta. So you've got this constant thing, and this is a unit one, so I climb up by pi to get that, and then to get back again, I climb up another 2 pi. I climb up 2 pi altogether. First pi is about there, and then 2 pi would be that distance again. So this is giving you, with a equal to 1, it's giving you whatever the angle is that you've turned. If you've turned 2 pi, that's how far you've climbed. This one has only turned pi, so it's up there 3.14 units right now. And it's a lighthouse staircase, right? The old lighthouse with the spiral staircase that makes the helicoid. And they're absolutely flat, level. So this is an important piece of the story of complex variables. It's very key to a number of things, mostly involving series representations and integral transforms and all sorts of things like that. Okay, any questions about this? This is, I hope, it's really beautiful. We're trying to make it more beautiful by doing it in a nice graphic setting. So here's the basic idea: monopole field, only power law field whose integral depends on path of integration. Okay. Path goes around. Each time it goes around, it picks up another 2 pi. Okay. So if you want to go around n times, you'll pick up n times 2 pi. So there's now, if your contour, the path of integration, doesn't include the center, if you do not have the center inside your contour, well, the integral is 0. So that means you haven't climbed the staircase. You do your integral out here, you just come right back to the same place you started. But you go there, you're going to be up by pi, 2 pi, and 3 pi, and so forth. Okay. So this is a way to visualize something that's very important to understanding the behavior of analytic functions and their integrals. Okay, so this one just shows 2 examples here with this is a stereo drawing, like it's right out of the textbook. They're sitting right next to each other, asking you to look at them and see the 3D. Go ahead and put that up over here. And then these are the 2 kinds of curves that you get by using a real value of whatever you're multiplying this thing. This is for A equal 1, the amplitude equal to 1. If you make an I, then you get the vortex. Okay. As the actual field vectors make a vortex. Okay. So the streamlines then very definitely on the helicoid. Okay. For the plot of the phi. For the plot of A, it makes the morning glory. Okay. With the contour lines being what they should be for plotting the vector potential. So, see the vector potential here sitting in the position of the I, whereas here, let's see if that's right, F star, Z star. I wonder if I made a mistake on that. That looks like it might actually be a typo. XY, Y minus X. Oh, that's right. I log Z, that's right. Yeah, no, that is right. This has got the angle here. And this one has the angle here. Okay. All right, so what does this source do for us? This is the beginning of making all of the possible fields that have sources in them. This is the most elementary one. But here's one I want you to look at in the problems. This is what you get if you use a complex number, not just 0 or I, but a complex number, one is a combination of real and imaginary. And this is where you really need the 3D to see what it is, what this vortex is. And this is, some of you are working in astrophysics. This is a big galaxy search university. We're part with University of California, Irvine, and a bunch of other places in Europe that are trying to study galactic structure. And one of the most prominent parts of galactic structure are these whirlpools of density of various objects. We're in a fairly tame galaxy ourselves, but there are these others that are way far away that have this kind of structure. So this is something that's worth looking at. Now, at this point, probably it would be a good idea for me to mention something else that I've given you as a problem, and this is a sort of a funny representation of a tornado. It's just basically 2 Pepsi bottles with a narrow space nozzle in between, and if I invert it and then give it some angular momentum, I produce a curve that's sort of related to the one that we're plotting here, I'm going to ask you to figure out what that curve is. But basically, what is that water has in it right now is a situation where an atom moving closer to the radius doesn't change its angular momentum. That sounds a little paradoxical. How can I? But basically, the idea is out here it's going slowly in proportion to its radius. As it moves in, the velocity goes according to 1 over r. So that the angular momentum of it is preserved. And also, what's true of the surface, let's see if I can get a good one going here right away. Now if I go this way and then turn the thing this way, it completely destroys it immediately. If we could do that to a tornado, we might end the deaths caused by tornadoes. But I don't know how to shake something that big, right? You figured that out, and you've solved the tornado problem. You can see it's very sensitive to that, okay? But the surface I'm asking you to make also would have the property that if you were on a boat, riding in this vortex, you would be stuck at that radius. No tendency to slide up or down. And if somebody pushes you up, your angular momentum would be conserved, actually. So those are clues for you to figure that out. Now the other thing that's true about this is once I get a vortex like that going, and you go to a swimming pool and you could just go like that and make vortices. But those vortices, unless you're really skillful at making, don't go down very far. They go down and then there's a dip. Okay? I want you to figure that one out too, assuming that in the dip region the water is rotating rigidly. That is, it's obeying the velocity that it has is proportional to r. Okay, like a rigid fluid. So that's why I say this particular problem has a connection with a sophomore physics Earth, which comes in like that, then forms a little dip there. It's a parabola. Okay, so that is kind of a weird connection, but the tornado versus the sophomore physics Earth is what the last problem is on today's homework. And I hope that today's homework is not quite as puzzling as the one that you're handing in. And again, Friday's good for that. Okay, let's see if there's anything else here that I need to point out. You're free to draw these things with computers if you want. Here's what's called a physical dipole. And now we're back to using real numbers for the coefficients. Okay. So what I've got here is a monopole with a positive sign, this one, out here on this axis. Okay. And then I've got one with a negative sign right about there. So I've got two monopoles close to each other, separated by some distance, uppercase delta. Okay? And so that's the total distance from center to center, delta over 2. That's what is separating them. Okay? So if you add these two together, you get something in the denominator with a square of z, subtracting the distance, this delta, squared. Now, if you make this delta squared really, really, really small, it isn't too, you don't have to go too far before this becomes small enough to just have this thing squared. And that's the real point here, is that what we're doing here, and I've got it on that screen down here, but particularly I haven't pointed out here, is this is like a derivative. F of z plus delta minus f of z divided by delta, right? So the process of taking a derivative is what you do to produce higher multipoles in this way of looking at multipole field theory. Actually, if you're going to balance the thing, you go f of z plus delta over 2 minus f of z minus delta over 2, again letting delta approach 0 infinitesimal. Okay. So this will be what we call a dipole source, a point dipole source, but there's the physical one. Okay. And it's an interesting curve. Two morning glories meeting, but the question is, what happens when you bring delta, to 0, to essentially 0, very, very close to 0, and that is going to be a derivative. So basically, what it is, if you make that tiny, go ahead and say it here as well. If you make that tiny, then you get this. Okay. So the physical dipole had a nice, pleasant slope. This one just drops. The morning glory has a absolutely flat side to it, and then some curve here. So that's a circle. That's kind of neat. And this one has an absolutely steep slope over the origin, and then a curve that go out from that. And here we're plotting phi, so the phi red lines are the contours that climb up this pillar hill or sink into this one. The geometry of that is really quite striking. We're going to use that for things later on, but I thought you ought to see it right now just for the fun of it. So if you take a monopole and take a derivative with respect to z, and the z, of course, is complex, so you can go make the derivative point in any direction just by changing the parameters of the complex variable. In any case, you will be getting a dipole that points in some direction by doing that. Okay. And the integral of this, this potential for the quadrupole in this case, just to integrate that with, to integrate the force with respect to z, gives you a 1 over z for the potential. So the potential for this thing is that. Okay. Let's see if there's anything else I need to say about this. Oh yes. This, I guess, is right. If you're going to go ahead and write this thing out, I've written it out that way, then you get an expression like this, which we're going to see a lot of. This is a resonance function later on in the mechanics that we're going to be doing. But here it's just a very pretty picture that has as its real part that potential that we just looked at, and then as its imaginary part has something that's very similar but turned at 90 degrees to this one. Okay. And there's the geometry of it. There's the geometry of this thing. So I'll move that up to the top. There's the algebra. Here's the beautiful geometry. Look straight down on that thing. It's all circles. Every contour is a circle. This is quite striking. And it's a circle that has, well, basically Thales rectangles in there. Rectangle, okay, right there. It's a Thales rectangle containing a way to show how big is the distance to a particular point on the vector potential line, or another R right here that goes to the scalar potential lines. Okay, so these are all circles intersecting circles. So we're going to use that when we study resonance in Unit 4, and it's been used before. It's very old. All of the electronics shops used to have graph paper with intersecting, overlapping graphs of circles to calculate various resonant phenomena. The Smith chart is what it's called. Anybody see a Smith chart now? They actually glue them to the screens now of things that are doing the computation digitally to let you see where you are in a particular resonance. But that's coming later. We'll talk about that. In any case, this is beautiful. I think this is just gorgeous to see the equipotentials like this. Dipoles in 3-space don't do this. They're not circles. But in 2 dimensions, yes. Exactly. Okay. Cool, I think. Anyway, next stop. What do you do to make the quadrupole? You take a pair of 2 poles, 2 fingers, and basically what you do is you take one set, make a Xerox copy of it, change its sign, and put them on top of each other. That's a derivative, right? So that's exactly what we're doing here, is we're taking a derivative of a dipole and making a quadrupole. That's all we have to do. And that's what you get. So that's the force field for the quadrupole. Integrate that and you get the potential for the quadrupole, which is an A over Z squared. Okay. So this one really requires 3D to see pretty well. The circles get squashed. Okay, this is a quadrupole now, and this is something you really need to put your nose against this figure in the textbook or the lecture notes. If you have it on your screen right now, you can do that. But you'll see that now they're not circles anymore. And I've got 4 of them. I got a clover leaf. I've got a clover leaf of the vector potential, streamline potential, which is the vector potential, and the scalar potential are similarly shaped lobes of equal scalar potentials. Okay, so these are the functions that result from taking this extra derivative. So, you know, the next stop is 2 to the 3rd power, which is an 8-pole, and I don't know how far you have to go to get a pole dancer. I think all of these things are beautiful just by themselves, and we'll try to show them. I think the new program will do a much better job than that at the display of these higher multiple functions. Okay. See if there's anything else I need to say, but I think now we should probably do this little exercise here, and that involves series. We have talked about Taylor series and Maclaurin series a little bit, just in getting this set up, but it's also come up in other things, approximations to various functions. But here is what we're faced with. It is called a Laurent series. Taylor series sort of stops there. That's a nice Maclaurin series, actually, a power law series, where you would just add up the dipole at infinity, quadrupole at infinity. That's what we started with. There's our starting point, a force field equal to the z times the constant. We took that constant to be 1. And then here are some higher order guys, okay, that you get by integrating this z to make z squared, the octupole, and so forth. And the way I think most mathematicians, and I would say any physicist that works with these functions for any application, views these things as the source at infinity, at the south pole of a stereographic sphere, which we're going to draw a picture of in just a minute here. But basic idea is this series in principle goes forever. Next stop is the hexadecapole. never quite makes it to the pole dancer. But going the other way, okay, you're talking about sources that are at your home at z equals 0. Okay, you've got a monopole, a dipole, and a quadrupole that we've been showing pictures of here. Now we're adding them all up with varying constants to make, in principle, the idea is that you can make any field function and scalar function of a complex variable, just for things that are located at the origin or at the opposite of the origin. You see, that's the game that is played with complex variables quite regularly in scattering theory and all sorts of things. So this is the force field here. The integral of that is the scalar potential. It's easy to take that, find that integral. Integral of 1 over z, of course, is the thing we've been talking about here. Integral of a constant is just z, and so forth down the line to the higher powers, higher positive powers. Okay, now the all field terms except for the red one, the 1 over z, with the coefficient a sub minus 1, have a potential term of a 2 to the m pole. The this guy right here, okay, for the m less than 0, the negative powers, these guys right here, they correspond to something that's going at infinity. Now we're just talking about here m greater than 0, but you're at infinity for that. You're located at home for that one. So here's a typical series up to power of 3 or minus 3 and this is something I haven't bothered to plot because of the old computer just makes a mess of most of the things that you get here. We have the possibility now of looking at these things more closely and beautifully. So that is coming. Now, we could write this guy here in terms of the z that we've been working with, or we can sort of turn the whole globe over and work with the w, which is 1 over z. Okay, z is w to the minus 1 power and vice versa. W is z to the minus 1 power. So that's what we're going to do, and I apologize for not following this on the other screen there. Let's go ahead and here I'll point out what we are dealing with, that this guy corresponds to that guy, this guy corresponds to that guy, and so forth. So there's this relationship between things that live around and are very small for us, and I guess I'm in that camp. I study molecules, atoms, okay, little light waves that are micron-sized, okay, and then we have a number of people in this class that are going to go the other way. You're not interested in little things, you're interested in monsters out there, right? So this is a transformation of atomic physicists into astronomers and astronomers into atomic physicists, okay? 1 over z, right? That's how you walk into the 1 over z machine, you switch fields. Okay, bad joke. Anyway, the idea of geometricizing this, I think, is really cool. And this is what's called a stereographic projection. And we have a z-plane, the thing that we've mostly been working with, is 1 over w, sitting up here, and there's the unit circle sketched in right there, and there's another unit circle right down here, and those map into each other. But the idea is if I have a particular z right here, so origin is right there, and then vector point z is right located there, run a line all the way down to the South Pole, and then do a connection of a line through the North Pole And wherever that line intersected the globe, and you will point to W, which is 1 over Z. So for any Z, that's the transformation. Now that transformation, again, there's Thales geometry again, a rectangle in a circle, okay, and a half angle here corresponding to a whole angle that is actually where that point is there. So you have a whole angle theta right there, but this is half that angle right there. That's Thales geometry right there, making a mapping between a particular Z and a 1 over Z, W. So there's the transformation of the atomic physicist into the astronomer. And as the atomic physicist gets closer and closer to here, the astrophysicist is looking further and further at something that's really monstrous. Is that pretty clear what that represents there? Kind of a neat construction. So anyway, what we're doing here is just imagining a few simple cases. If, for example, I have a positive charged monopole on the North Pole, okay, its force lines go around and converge on the South Pole. So that's a pretty easy transformation right there between the two kinds of monopoles. And that's basically because it's a logarithm, so you just use the same function. But when it comes time to do the other ones, you have a cross-ton talking here. If I have a dipole field at the North Pole, and that's the one that has the circles and sort of if I was either drawing the vector potential or the scalar potential, which would be in the other direction, 90 degrees, I would have a bunch of circles, and they all get bigger and bigger and bigger until they go down to the South Pole to make a constant field down there. Okay? So, all of these things, a quadrupole field centered at the North Pole makes a quadratic field, that's the W squared, if you're talking about the potential, or it's just W if you're talking about the force field. Anyway, this is a neat way to catalog all of the functions and the relationships between their inverses, all of the polynomial functions and their relations. So I hold that up as yet another visualization aid for something that otherwise is quite abstract and usually unreachable by most physicists. This is a doorway to understanding some of that. And here's where it's used. This is just some practical ideas here. As again, it says of all the 2 to the m poles that you can possibly make, only m equals 0 has a non-zero loop interval around the origin. Okay, and of course that's because of the logarithm that the potential gives. So when I do the integral of the force to get that phi, I get a value. That's a constant, just whatever the constant is, times 2 pi I. That's what it costs to go once around the origin, is 2 pi in the I direction, in the imaginary direction. So I solve for that coefficient, and that's an important beginning of what's called Cauchy's interval. And that's what's needed in order to extend this stuff to a calculus that lets us do integrals easily. This is really, I haven't mentioned this in the list of good things about complex variables, but easy integrals is probably a good way to say it. I've been saying easy everything, right? This makes it easier to do some integrals that come up in all kinds of physics, particularly field theory. But the basic idea is that each of these coefficients, that represent the dipole, quadrupole, octupole, whether it's at home or at infinity, they all correspond to functions that have these as coefficients. So this is eventually a way to solve for the coefficients of the series if you know the function. If you know the function of z this is a way that you get that, the values of that. So it's all based on the fact that, as I say here, you assume any circle around Z over A, and this function here will give you a value that you find very easily by just considering a very tiny circle, so that A can be treated, let the thing be a radius, and just take it outside. So you get 1 over Z minus A, and that's 2 pi I times the value of the function that you have here at the point A, wherever that might be. And that becomes, that basic idea of that thing, that's called the Cauchy integral theorem. So this is a neat relationship which we then use. The repeated A derivatives of this thing, just take a derivative of, inside the integral sign. That's one of Feynman's great tricks that he mentions in his book, that lists all of the tricks that he needed to get through graduate school. The expressions for the various derivatives of the Cauchy integral come there. And that gives you a Taylor-Lorentz power series. Now, for n greater than 0, it's just 1 over n factorial times the derivative of the function, the nth derivative of the function. So that's a Maclaurin, or Taylor if you were moving the a value around a function. So the coefficients are obtained for n greater than 0, but for n less than 0, they are these integrals. And those can also be, well, written that way. That basically, this is a particular series that you would get in general if you apply all of this to some function. So it's got negative powers, and they can be, the more negative powers you got, the more work you have to do working with something like this, but basically that's what it's doing. So here are all of the force or scalar potential terms for quadrupole at infinity, octupole at infinity, hexadecapole at infinity, and so forth, down to the dipole infinity. Then the monopole, well, it's either infinity or 0. Then here's the dipole at 0, the quadrupole at 0, and so forth. That's the Lorentz series in physics with a physical interpretation. All right, now this is sort of a, we've got enough time, I think, to just bear with me, a hobby, okay? A hobby that I've kind of dropped. I haven't used it much lately, but it was a big help at one point. The idea of these Riemann quotient derivative relations, they work for both the potential and the field. Okay, either one of them do satisfy these things. So that's an important idea. And it's also important because if you're doing a mapping, and that's the other thing that this application that TC is putting together that will do very nicely. We're just having it work this morning a little bit. It's also there, but it's not anywhere near as developed enough where most of the functions come out looking sort of terrible. But in any case, if you have a mapping between a particular xy complex space and another one, well, the function that does that, w of z, has some properties that relate to our mechanics. The Jacobian for a mapping, it's an analytic function mapping, so it's going to have the properties. It's going to have a complex derivative that looks like that, and what's neat is there's a relationship between that derivative. It equals the Jacobian determinant. So here's the Jacobian, take the determinant of that, and you get the dw dz for any function w of z. Okay, now I'm using w here don't necessarily mean w equal 1 over z, so don't make that mistake here. but it could be. It could be any function of z, analytic function of z, and you get this relationship between the Jacobian. So basically what it boils down to, and I think this is an important result, is the differential. If you have a thing here, you move it a little bit like this, it's going to move according to the square root of the Jacobian, and it's going to move in the direction e to the I theta that particular number has. So I think that's a cool result to be aware of when you using this stuff. And there's a typical mapping, and I'm asking you to look at this mapping a little bit more critical in a problem. And also its inverse. Basic idea is that if I make this mapping on the computer and start walking this way, you'll see a point on that program walking around one of these. So you're basically taking this thing and scrunching it in a particular way to make this coordinate system. Now this is the flow chart for water coming out of a pier. If there's a pier right here blocking all of the water and it ends there, those could be the streamlines around this one, and these would be the potentials associated with that. The streaming potential would be in the direction of the flow, and then the scalar potential would be the other curves. But there are, of course, applications for our mechanics that use parabolic and paraboloidal coordinates and solve some pretty nasty problems, closed form and really beautiful. But we get this coordinate system really easily by complex variables. So easy coordinate systems, that was another advertising point for the use of this stuff. Okay, I'm getting behind on the other screen here. There's all the Cauchy stuff. I'm sorry about that. I'm used to running two screens at once. But that is a key thing. And this is another case. If you do the inverse, of this mapping, you get this funny thing right here. Okay, which has equilateral hyperbolas as opposed to ones that are trained to the axes. So both of these mappings are worth getting familiar with for mechanics later on. Now this is the crazy part. What I'm saying here is if you want to have a continuous set of sources, not sources that are dot here, dot there, or two dots here, or quadrupole here, that's all fine for some applications, but what if you want to just smear the space with sources? This is the way you do it, at least one way to do that. And it's going to involve force field function that is not an analytic function of z or z star, it's a function of both. It's a non-analytic function of the complex independent variable. Okay? So, and it'll be a function of each of the components, a function of x and y, just like we've been having already, but it will be very different functions. It will be functions that represent the location of sources. So the sources won't be zero everywhere except at singularities, they'll be continuous. And there'll be two kinds of them. One of them is sort of longitudinal, it's like charge, and the other one is like a current or something. And I use those symbols appropriately. So what we do is we generalize these force-free equations here, the derivative of f of z star being 0 as a derivative of the f of z with respect to z star. Those are both 0, and those are based on relations that we've looked at and that gave us a coefficient here that was a divergence of f and a coefficient here that's the curl of f. Now those things, those divergences aren't going to be, or those curls, they're not going to be 0 everywhere. They're going to be non-zero practically everywhere. So we're going to be writing source equations like this. Instead of putting 0, we're going to have source. And we're going to have a source star, and we're going to have a source that's not starred. Okay, that's a conjugate of this one, so we still only have to work with one source, but it's more complicated than just working with 0. So we have a field equation that looks like this, then we'll have a potential field that looks like that. And remember how you get a potential from a force, you have the force being given as a gradient, or you have the force being given as an integral. The idea being that we can take an integral with respect to these z's, even if they're not analytic. So the basic idea here of getting the source equal to derivative of the f is sort of summed up here. The idea is that I get an equation that's going to let me find these things, these sources, given the fields, or else find, given the sources, some fields. And that is, and I try to keep up over here with all of this. So the basic idea comes fairly quickly here, and these are not zero in general for these. So I have to give an example of this, and that's what I'll do here. But basically, instead of having Laplace's equations, we're going to have, well, start with no zero here. This is going to be a source density of some kind. It makes a non-orthogonal flow diagram. This one will do another diagram that's sort of conjugate to this one that involves the current sources. And that is what we're after here. In other words, we're going to be making here something that's a gradient of a scalar, and then something else that's a curl of a vector potential, both on top of each other. And hope it works. And most of the time it does. That's what's really neat. So what we're getting here is the longitudinal part of a general vector flow field, and the transferred force field that is written as a curl of A. Kind of like a magnetic field here and an electric field here. We're getting both at once. So this is a little bit analogous, you see. Here's the source, okay, and we take that source and integrate it to get the field, okay, and then what do you do with the field, okay, integrate that again, we're going this way now, to get the potential, okay, and then there's a relationship between the potential and the field that involves two derivatives. We could have gone the other way. I could have had the vector force field here. The derivative with respect to z is the source, and similarly the derivative of the scalar potential is the force. And this is more than the scalar potential. This has got two parts to it, scalar and vector. Okay, so this is analogous in sort of a who drives who to Newton equations. Here's your kind of your source, your acceleration, which in our superball analogy that I made, we didn't have any of this. It was just straight linear velocity until, boom, something hit. That was a lot of acceleration, but it was only a brief one, and then more a different constant velocity for 2, 3, 4 balls doing all sorts of things. Okay, so this includes now the full study of mechanics, where we've got variable acceleration, variable position, and variable velocity in any number of dimensions, and that's what we're about to head into as we go into Unit 2 and 3, sort of together. All right, well, I guess I've got to show an example just for the heck of it. This is one that has a density, charge density of 4 times the x-coordinate, and the current that's minus 4 times the y-coordinate. That's a pretty simple setup. So what do you have to do to get this thing? You've got to integrate this thing with respect to z, and you end up with a sort of a collection of x's and y's, like we would have gotten doing an analytic thing. But this one gives me a phi here and an a here that are really quite different. And that's what we're going to look at. We're going to look at plots of those things. But we check them to see if I get the curl of A, it gives me a thing like that. That's giving me the transverse force. So the longitudinal force is gotten by the gradient of the scalar part of the thing. This is the curl of the vector part of the thing. So we're getting vectors here. They're really quite different. The longitudinal vectors and the transverse vectors are not the same as they were in what we did before. And the total force field summed up is a thing like this. And it's not too different from what we got before, except for the sign here. But anyway, that field, I'm going to show that field, is really quite horrendous. This is the field that has curl and divergence virtually everywhere. Actually, it's none of it right here. But everywhere else, it's got lots of divergence and lots of curl. There's the part of it that's got just a scalar potential, and this force, these are the vectors that are gradients of that thing, and then those are the vectors that are curl of this. So there's the transverse force field there. This is the scalar force field. The longitudinal is a good name for that. The diverging part, and this is the curling part. That's another way to say it. Okay. Well, put those two on top of each other, and you've got a GCC coordinate system. These are not orthogonal, nor should you expect them to be. Only if I turn this all back into an analytic thing would I have that orthogonality. Here I don't. Okay. So this monster, that's just a plot of it for the few points, this monster is tamed by this weird use of non-analytic functions. I've said enough. Your eyes are starting to glaze over, I bet. But this is, I think it's a cool thing to know about if you're working with, you know, coordinate systems for weird things that do weird motions in small spaces. Okay, we'll see you next Monday, and as I said, you're free to turn in to my mailbox by Friday the homework. And if you do it right now, you get those extra 5 points or so.